Hey everybody, and welcome to this video. So today we will implement a regularization technique called Mixup. Just for the record, it has been around for a couple of years now, and it is definitely not as mainstream as dropout or weight decay. However, it is pretty easy to grasp and simple to implement, which is probably the main reason why I decided to go for this topic. Anyway, what you see on the screen is the official GitHub repo for the paper called Mixup Beyond Empirical Risk Minimization. For the rest of the video, I will refer to the technique proposed in this paper as input mixup. And here you can see the source code of another paper, which is called Manifold Mixup, Better Representations by Interpolating Hidden States. These two papers are very much related because one can actually see the input mixup as a special case of the more general manifold mixup. Anyway, before I start explaining things in more detail, let me just give you a small disclaimer. I did not really spend too much time going through the official implementations and mostly just wrote my implementation from scratch. It is totally possible that there are bugs, misinterpretations, and simplifications. You should always refer to the original code and paper. Lastly, all the credits go to the authors and contributors. Let me start with a high-level explanation of the input mixing. What you see on the screen is a section from the paper that explains the main idea behind this technique. Most importantly, we are dealing with a general classification problem. We start by taking two samples from our dataset and we mix them together. This mixing is done in a linear fashion, and what is really important is that it is applied both on the feature vectors and the target labels. The coefficient lambda is sampled randomly, however, it is always going to be in the interval 0 and 1. The authors claim that input mixup can help improve generalization of our model and that it can yield smoother estimates of uncertainty. Here we see a section from the Manifold Mixup paper that summarizes the method. The major difference compared to the input mixup is that not only we can mix the input features, but also an arbitrary hidden representation produced by our neural network. This mixed representation is then reinserted back to the network and the remaining steps of the forward pass are run. Note that here not only we sample the lambda randomly, but we also sample the hidden layer where the mixup will happen. Under this setup, input mixup is just a special case of manifold mixup in case we restrict the hidden layer to be 0, or in other words, just the input feature vector. The authors claim that similarly to input mixup, it helps with generalization and that it leads to smoother decision boundaries. Additionally, they also claim that it has a positive effect on the hidden representations because it flattens them. And here flattening means that the number of directions with significant variance is reduced. Anyway, let us now start with the implementation. I thought it would be nice to visualize how input mixup and manifold mixup behave on a relatively simple but tricky dataset. Namely, we will use the two-spiral dataset. It is a binary classification with only two features, the x and y coordinates. We will use a vanilla multilayer perceptron and deploy different regularization strategies during the training and then investigate what effect they have. Alright, so let us start with writing some utilities. So first of all, we will write our neural network and it's going to be a multilayer perceptron for binary classification. However, we will try to implement the forward method in a way that we could use it for mixup. Alright, so the first parameter is going to be number of input features. In our example, it's going to be 2, but here I keep it general. Hidden dimensions will determine the architecture of our multi-layer perceptron. And finally, P is the dropout probability. Note that by default, we are going to set this equal to 0, and therefore no dropout is going to be applied. Internally, we'll store the hidden layers inside of the module list. And each of the hidden layers is going to be a linear layer followed by a leaky ReLU and a dropout module. And finally, after all the hidden layers, we will have the classifier layer, which is just a linear module. So here we create a new tuple that is going to be all the hidden dimensions tuple, prepended with the number of input features tuple. Here we just count the number of hidden layers. So here we use the module list to store all the hidden layers, and yeah, the actual layer is nothing else than a linear module, activation, and dropout. And finally, we create the classifier, and it takes the last hidden representation and it maps it into a single number. And that is because we are assuming that we have a binary classification. All right, so first of all, we provide our input tensor. However, then we can also specify two parameters, start and end, and they will determine what hidden layer we start with and what hidden layer we end with. By default, we are going to go through all the hidden layers and then run through the classifier at the end. However, by changing these parameters, we can restrict ourselves to just a portion of the architecture. One special case is when we set both the start and the end equal to 0. And under this setup, the forward is just going to return the input X. So in a way, it's a no-op or an identity mapping. As you can see here, we slice our hidden layers based on the start and end, and then we just iteratively apply all the selected modules. And if the end parameter is going to be none, then we also run our classifier. That's it. And this code will actually enable us to implement the manifold mixing, because we will just select randomly a hidden layer inside of our network. And then we just split our forward pass into two parts. The first part is going to take an input tensor and transform it into a hidden representation. And the second part is going to take hidden representation and classify it. All right, now we will subclass the dataset class of PyTorch. And it is pretty straightforward because we want to take the two classification matrices X and Y, and we just wrap them inside of this data set, and this will allow us to do batching and use data loaders. So first of all, we do input validation, and most notably, we make sure that all targets are either a 0 or a 1. And finally, we just store the X and Y matrices internally. So the length of our dataset is nothing else than the number of samples. And when we want to get a specific sample from our dataset, we return a tuple where the first element is the feature vector and the second element is the target. Anyway, so we have just written a wrapper for the X and Y matrices. However, now let us also write the actual data generating function. All right, so we will specify the number of samples we want to generate, and the label distribution is going to be 50% the first spiral and 50% the second spiral. We can add some noise if we want. We can control how many cycles or revolutions the spirals are going to have, but I guess by default we will stick to 2. And finally, this function returns the X and Y. For simplicity, we enforce the number of samples to be an even number. And as mentioned, the two classes will be perfectly balanced. One way to understand what I just wrote is to start thinking in polar coordinates. And that means that to specify a coordinate, we don't use X and Y elements anymore. However, we use an angle and a radius with respect to the origin. And if you think about drawing a circle in polar coordinates, it means nothing else than keeping the same radius but changing the angle. However, if you want to create a spiral, we can change the angle, and at the same time we can increase the radius. And yeah, that's the idea. And the difference between the first and the second spiral is that the second spiral starts at a different angle. Here we just stack both of the spirals together, and this way we create the feature matrix for machine learning. And here we also define the targets. So here the goal is to randomly shuffle all the data points, because currently they are just consecutive, because the first 50% of the data set is class 0, spiral 0, and the rest is the second spiral. And finally, we apply the shuffling, and also we add random noise to the feature matrix. The last utility function we want to implement is related to generating visualizations. And here I was inspired by scikit-learn examples. In short, we want to understand the predictions of our classifier on a grid of points. All right, so we pass our neural network and also all the train and test data. And we will yield a couple of different figures. And the idea is to use this function every now and then when we're training for evaluation purposes. Anyway, we imply the device, the D-type, and we define some color maps. Here we computed the X and Y limits based on the test data, and in our case, the test data will be way bigger than the trained data. Here we generated a rectangular grid of coordinates. And we take the entire grid and run it through our network, and that way we'll get the logits. And note that here we're not doing any batching, and we're kind of hoping that everything fits in memory, which is the case for our small example. And here we turn the logits that were the output of our network into probabilities by running them through the sigmoid activation. All right, so the first figure that we're going to return is just a scatter plot of all the test data. And note that this doesn't really depend on the model at all and is going to stay constant. The second plot that we're going to generate is a contour plot, and it will help us visualize the decision boundaries and how confident our model is. And finally, we overlay the contour plot with a scatter plot of our training data. And this will hopefully help us understand why the model made a decision like this and whether it overfits. All right, and now we would like to write our training script. All right, so let's create a command line interface. All right, so let me point out some interesting arguments. This parameter will determine the range from which we sample the hidden layers. And by default, it's none, and that means that the hidden layer can be anything. And here you can see that we have a mix-up flag, and the idea is that we need to specify this flag in order to use this technique. Similarly, the dropout probability is set to 0, and we need to specifically change it in order to employ dropout. And finally, the same logic with weight decay. By default, it is 0, so there is no weight decay, and we can modify it if we want. All right, and now we can write the logic. All right, so we parse all the arguments, and then we define the device and the D-type, and know that for this experiment, that is enough to do everything on a CPU. We set the random generator seed for both NumPy and Torch. And here we use our generate spirals function that we implemented. We don't introduce any noise whatsoever. And here we use scikit-learn's train test split. What's interesting here is that the test size is going to be 90%. And we do this to kind of simulate an environment where we don't have a lot of training samples. However, we have a lot of test samples so that the evaluation is more robust. So here we cast the test features into a torch tensor, and we do this for convenience because we need to use it as an input to a torch model. Here we construct our custom dataset wrapper, and the main reason why we do this is to be able to create a data loader that is going to create batches of training examples. All right, so here we create a training data loader, and we see that the batch size is actually equal to twice the batch size that we provided through the command line. And this is related to how we're going to implement the mix-up. Here we instantiate our multilayer perceptron using some of the CLI arguments. So here we instantiate an optimizer. And our loss function is going to be the binary cross entropy with logits. Here we create a summary writer for TensorBoard, and we dump all the CLI arguments as text. All right, and here we start writing our training loop. First of all, we make sure that both the features and the targets are on the right device and have the right d-type. And here we will have an if statement. First of all, we implement the behavior with mixup, and then in the other branch of the if statement, we will implement the behavior without mixup. First of all, we determine the range of hidden layers that we can randomly sample from. And here we sample one of the layers. Then we sample the lambda coefficient that will be used in the convex combination. And as you can see, we are sampling from the beta distribution where both of the parameters are equal to 2. I mean, this is also a hyperparameter. I just hard-coded it. What's important is that the support of this distribution is 0 and 1, which is exactly what we want. And here we track both k and lambda with TensorBoard. And now we do the first part of the forward pass. We take the input features and we run the forward pass all the way until the kth hidden layer. Now we actually use the fact that our batch is actually twice as big as what was desired. And that is because we are going to split it in half and then mix the first sub-batch with the second sub-batch. And this mixing is nothing else than a convex combination. Another way to implement this would be to have a single batch and then just shuffle the samples inside of it. But yeah, I just went for this implementation. Clearly, this implementation is more memory heavy. Anyway. And here we do the same mixing with the targets. And since the targets are either 0 or 1, their convex combination is going to lie in the interval 0, 1. And now we take the mixed hidden representation and send it through the remaining hidden layers together with the final classification layer. And in case we don't want to use mixup, we just run a standard forward pass across the entire network, and that's it. Note that I threw away half of the samples here to make things comparable to the mixup. However, I'm not sure if it makes sense. It's definitely very wasteful. And here we have the standard torch boilerplate. We zero all gradients, we compute new ones, and we take a gradient descent step. Here we track the training loss with TensorBoard. And here, every 2,500 steps, we will track a bunch of different things. Specifically, we will make use of the generate prediction image function that we wrote. And here we compute the accuracy on the test set and also the loss on the entire test set. And as you can see, we do the inference on the entire test set at once without any batching. Again, in our small example, we are not going to run out of memory. And here we track both of the values with TensorBoard. And finally, we switch the model back to the training mode. And this is actually relevant for things like dropout. All right, and I believe we are done. I have prepared a shell script that launches multiple experiments. I used the CLI that we just wrote, and yeah, let me quickly explain the models. The first experiment applies no regularization. The second one uses weight decay. And by the way, I was looking for the right number for quite a long time. Here we have a dropout regularization. Here we have the mix-up. And since we are not specifying any layer range, the hidden layer can be anything, including the input features themselves. In this experiment, we only apply mix-up on the input. Finally, in the last experiment, we only apply mix-up in the hidden layers, so no input mix-up is taking place. By the way, this seed determines how the dataset looks like, and it really makes a big difference. Let us now inspect the results. First of all, I filtered those experiments corresponding to the random seed 123. If we look at the training loss, we see that when we apply no regularization, here it is the dark red color, the network is capable of having a loss very close to 0. One can view this as a proof that our network has enough capacity to learn the dataset. However, we need to regularize it somehow. And the training loss behaves similarly across different random seeds. If we look at the test loss, we right away see that applying no regularization leads to overfitting. Looking at the test accuracy, one might be tempted to conclude that dropout dominates all the other approaches. However, this metric seems to change quite a bit with different random seeds. Anyway, it seems like in general, dropout and mixup give the best result, whereas the input mixup leads to underfitting. Here we can see how the hidden layer was sampled during the training for different regularization schemes. Namely, for input mixup, it was always 0 because we always applied the mixup to the input features. For mixup, it was anything from 0 to 3, and that is because we have 3 hidden layers. And finally, we see that for the hidden layers mixup, it was only 1 and 2 and 3, and that is because we disabled mixing of the input features. And here you can see the plot of lambda over training. Just to remind you, we sampled it from the beta distribution, and the values are always in the range 0 and 1. Let us now move to images. First of all, this is how the test set looks like. It is the same for all experiments, and it is way bigger than the training set because we wanted to simulate insufficient number of training samples. Here we can see the training set scatter plot together with the model predictions as the contour plot. Wide regions represent regions of uncertainty, or in other words, regions where the predicted probability was close to 0.5. So let us inspect each of the experiments one by one. Here we see the model with no regularization. The main thing to note here is that the decision boundaries are very thin and that there are basically no regions of uncertainty. When we look at the mix-up, we see that a way bigger portion of the plot is occupied by wide regions. More specifically, these regions of uncertainty correspond to regions where we did not have enough training samples. Weight decay also seems to introduce regions of uncertainty, however, it might lead to underfitting. And as mentioned before, the actual weight decay size is a hyperparameter, and I had to run multiple experiments to find a reasonable value. So definitely take this plot with a grain of salt, because a small change in the value of the weight decay will probably influence the results a lot. The input mixup clearly leads to a model that is very uncertain about its predictions. The main reason for this is that the spirals are not a convex set. And what happens during training is that the same input feature vector can have completely different labels at different training steps. Here we see a case where we apply mixup to the hidden layers only. It seems like the model gets more confident compared to the standard mixup, however, still less confident than without regularization. Finally, dropout seems to work really nicely for this given dataset, and as you can see, the predictions are actually forming nice regions. Anyway, as mentioned before, changing the training set by modifying the random seed or changing the number of samples will have a huge effect on the results. Let me switch to the seed 124. As you can see, dropout doesn't really seem to do that well this time around. Anyway, looking at these experiments, I would conclude that mixup is definitely an interesting and potentially useful regularization technique. Let me also point out that the authors mention that mixup leads to flattened representations. However, I did not really cover it. And that's all I have for today. I hope you enjoyed it. All the credits go to the authors. Feel free to leave a comment or ask any questions. And if you have any cool topic suggestions, or you just want to chat, I would more than recommend the Discord server for this channel. You can find the link in the description. Thank you very much for watching this video, and I will see you soon.